Okay. All right, so you figured out, I guess I told you that if you don't understand how to do electron configurations, you won't understand the Grotrian diagrams, and then you won't understand term symbols. And so now after all of that, you realize, yeah, that's true. So are there any nuances or questions you have about making up these electron configurations? Do you remember sort of applying it to the periodic table and seeing the different groups up there? So you can look at, let's just say, platinum. You see there, PT next to gold, platinum. And so that's in that D block. And so what's the top row of the D elements? That's 3D, and then 4D, 5D. So we know that platinum has a 5D electrons in it in its valence shell. So those outermost electrons are 5D. And you can see that right here in this screen here. So this is the 5D. So if we wanted to do platinum, we would go back to the previous core. So that would be the xenon core. And then we come into the periodic table here on row 6. So we know the next is 6s. We're way past the 6s. So let's go ahead and fill it up with 2 electrons. And then platinum's got these F blocks here. So it's past all of the F block elements. So we know that is 4F14. Now, how do we know it's 4F if we didn't see these numbers here? Well, the first available D is 3D. The first available F is 4F. Okay. The first available P's are 2P. So you start with 1S, and then the next time you're going to have a more interesting set of orbitals is the 2P group, and then you have a 3D group and a 4F group. So it's just based on those restrictions for the quantum numbers. And then we're in this D group. So let's count up 1, 2, 3, 4, 5, 6, 7, 8. So that would be 5D8. So just knowing how the periodic table is constructed, then we can come up with these different elements. Now, that is essentially how they came up with this strange shape to the periodic table. It wasn't like Tetris where they just, that little meme that I have. This is how they made the periodic table. It's just looking at the energies of the elements. Now, what gives the elements their energies? It's the protons and the electrons balanced. And so if you change the electron cloud's energy, you're changing the energy of the whole atom, and that's where the Grotrian diagram comes in. Do you want me to do a different one? Pick a strange one? Manganese? Yeah, okay, very good. Manganese. So here we are, manganese, and so we go back to the previous noble gas, and so it's an argon core. And then we come into the periodic table on row 4, so we know it's a 4s. And it's kind of close to the middle, so I'm going to hold off on the s's in case I have one of those exceptions. Or let's go ahead and let's do it the regular way and then see if we can make it better. So we'll go ahead and do 4s2, and then we're at 1, 2, 3, 4, 5. So that's perfect, actually, the 3d5. So it has a half-filled d subshell. So it's a very stable element electron configuration. Notice how chromium is 1 to the left, so that is 1 fewer electron. And so it's going to take that electron out of the s orbital so it can keep that half-filled d subshell. So looking at chromium and manganese. Now, looking at these 2 electron configurations, what do you think one of, there's multiple, but what do you think one of the preferred oxidation states is for manganese? So this one right here is also for manganese cation. Right? If I take an electron out of manganese, then it's isoelectronic with chromium. And I'm not just giving you random facts there. That's on the test. Okay. So the idea of taking electrons away, you can come up with electron configurations for cations and anions and so on. It's pretty rare that you can make negative metals, right? But if we had vanadium anion, so V minus would also equal chromium. Does that make sense? Because we're one to the left of chromium. So if I add an electron to vanadium, it has the same number of electrons as chromium, and so that stable electron cloud of 4s1 3d5 would apply to vanadium minus 1. So it would be isoelectronic with chromium. Yes?
Will an atom ever transfer more than one electron to achieve a half or full subshell? Like for vanadium, you can't just completely take out all of 4s and just go for 3d to 5?
No.
Okay.
So that's a great question. So let's look at vanadium here. So it's vanadium equals argon core. Took me a second to understand what you were asking. And so it's past the 4s, 2, and then 3d3. So he's asking, could you just take both of those electrons and stick them in the 3 to get the 3d5? Okay, that seems to raise it up too high in energy. Okay, so this would be the lower energy form. That kind of thing may happen. I didn't see it. Let's look at the next slide, because it has from the OpenStax, it has all of the different electron configurations, at least for the valence electrons. And so here we have, this one is taking the d electron that shows up here. So this is 6s2 5d1. Is everybody comfortable with that for lanthanum? But then we go to cerium, and then that d electron has been pulled into the f subshell. But it pulled one electron into the F. And so this lanthanum and actinium would be ones that I'm not going to ask you those, just because if you're looking at this, I mean, you might get it right, okay? But it's actually, what am I trying to say? That's in the 5D, and that's why they put it here instead of making it the first F electron. You see how the 3Ds are added before you get to the 4Fs, okay? And so when you get down here and you have the 3Ds are added before you get to the 4Ps. Down here you have the 6S, and if you follow this Aufbau filling scheme, the next electron should be 4F, right? So if you're following this scheme, you would get lanthanum wrong. You would put a 4F1 there. And in actuality, when they look at the actual elements and their configurations, the 5D orbital seems to come in first. And then you fill in the Fs, and then you go back to the Ds. So I'm not going to ask you these guys right here, because if you follow that little Aufbau filling scheme, you'd get it wrong. Okay.
I'm not understanding why in the Ds, why it goes like one row, it's the 4D row, has the S1s primarily through the whole row, but then the top row and the row below that have a lot of S2s.
Okay, yeah, good question. Oh, here, palladium does what you were saying, Warren. Palladium steals both the S electrons.
Cool.
Yeah, so I guess it's possible, yeah. And so the reason that's happening is because these you've got a whole nother shell and you're further out from the nucleus, and so the energy difference between those s orbitals and d orbitals is much closer together. Remember, as we go up in these orbitals, they get closer together, even from the Grotrian diagram. And so the difference between that palladium having a 5s2 4d8, similar to this, a 4s2 3d8, and the 4d10 is very, very small. And so that's enough of an energy difference for it to steal those 2s electrons and drop down to be the lowest electron configuration. So that's the lowest energy electron configuration for palladium. The only exceptions that I'm really going to push on you guys are the ones like the chromium, molybdenum row, because those are or column, because those are standard, and then the D10s, would be a D9. So definitely know those, and definitely know isoelectronic. Like if I make a cation, it's isoelectronic with an element to the left. Okay, like I wouldn't have known palladium was that, and so I didn't go through every option for you guys, every possible exception. But these are such strong exceptions, the chromium and the copper group, that you need to know those for sure.
So we're more so paying attention to the ones that have like a uniform pattern.
Yeah. So these exceptions to the exceptions are a little more difficult. So I'm just mainly talking about that chromium group and the copper group, because again, it'll steal one s electron over to get a full D or a half D. Okay. And then the rest are pretty straightforward. And then again, focusing on that isoelectronic, if you have a cation, so think about oxygen anion, so O2 minus. Why is that such a stable ion? Because I've gone 2 to the right and it looks like neon. So O2 minus is just equal to neon electronically. So it's isoelectronic with a noble gas. And same with all the halogens, -1. All of those halogens being -1, they have a noble gas configuration. All right, let's move on so we don't run out of time. So then we have the Grotrian diagram for Mercury, and I just kind of went through all of these different ones. What I would like for you to know how to do is if you look down here at the bottom and you see 5D10, 6SNF, right? So you need to know then what that tells us about this state here. Okay. So connecting what's in that Grotrian diagram at the bottom with what's in those different columns in terms of their electron configuration. So this first one is 6SNP, and so we have 6S1NP. Okay, N would be the first available P shell for Mercury. And so we're down here at Mercury. And so then that first available P subshell that's empty, all those others are filled with electrons. So the first one that's empty is going to be on row 6. And remember, row 6 has 6 S's and 6 P's. So that's the 6P subshell. And so that's going to be our ground state for Mercury. I'll go through all of these. Let's get up to the one where I was asking questions about. So we have that, let's see, 5D10, 6SNF. Did I miss this 6S? It should be in here. So this 6S1. No.
What is the ground state of 6P?
Oh, that's messed up. Wow, I discovered an error. Okay, let me scratch that one out. That level is actually for this column right here. So let's do this one right here. So that is xenon core. And then we have that 4F14. And then the 5D10, those are all filled. And then this says 6S, 6S1, the 1 is just eliminated down there. And then we have NF. And so what's the next F subshell? We did that 4F, so the next one's the 5F. And so it would be 5F1. And so that would be the electron configuration for that one. And I know that because of this right here. See, it gets me up through 5D10. It's saying everything below that is filled. Here's the last filled subshell, the 5D10, and then we start with the unfilled stuff. Yes?
What is the ground state of 6P1?
It's just, who knows? It's the lowest energy electron configuration. So for Mercury, I would have gotten that one wrong too. I would have said 6S2, 5D10, and that would have been it, right? And so what it's done is it's pulled one of those electrons out of the s orbital and stuck it in the p orbital. So this one up here is what I would have, if I asked you this on the test, I would count this one correct, right? When you go to science, you actually do the experiment and you look at what the lowest energy electron cloud is around Mercury, and it happens to be the 6S1, 6P1. Because this is the energy, and it's quite a bit of energy. This is 60,000 wave numbers. This is 36,000 wave numbers. So it's like 30,000 wave numbers lower in energy by just pulling that electron out of the 6s and putting it in the 6p. Who knows, right? This is just what's going on with those electron clouds that are so far from the nucleus. Yeah, it's hard to know the rhyme or reason for it. Yeah, but knowing this, what I'm asking you here, is if you have this little designation, 5d10, 6s, np, could you come up with this electron configuration? You've got everything up through the 5d10, 6s, np. So 6s1, and then n, what is this n? The first available p subshell is going to be the 6, and so that's 6 is, n is equal to 6 for this first level, p1. But remember, this designation gets this whole column. And so the only difference between that one and this one is it's the same, and then we have 7p1. And then this one is 8p1. Makes sense? So that whole column is 5d10, 6s, np1. And so that n, it just increases going up. That's the principal quantum number. Yes?
Do you have more of these protein diagrams that we can practice?
Just really all the ones that are in the notes. We have sodium in the notes, we have mercury in the notes, and we have helium in the notes. And so just become familiar with those. Yeah. Okay. So then once we have those electron configurations, we can make up the term symbols. And so this is the NP2. I'm going to just go through this one again, and then we may do one by hand. That's a little different. Okay. So remember, we're only worried about the electrons in the partially filled subshell. So these P2 electrons. That's why sometimes we can just summarize this problem by just saying it's a P2 system. And so since we have electrons, we've got 3 orbitals there. We've got a couple of electrons in there. However we put these in, like we could put them like this, where they're both spin up in the first 2. If we did M sub L equals -1, 0, and 1. You know, what if we put them in the 0 and 1? What if we put them in the -1 and the 1? We have all these different permutations, and we're coming up with the term symbols that describe all of those particular cases. But the end result is we're looking at this electron here and this electron here. So this one, we need to know L1 for this electron and L2 for this electron. So that's what we mean by L1 and L2. What's the angular momentum for electron 1? What's the angular momentum for electron 2? And they're both in P subshells. So L1 equals L2 equals 1. So that's where we get this 1 and 1. So for electron 1, we have this. For electron 2, we have that. And that's the maximum value. That adds up to 2, and then down to 0. And then we just have integers in between. So 2, 1, 0 are our full range of L's. And since that's the angular momentum quantum number, we have those letters that we use. So capital D, capital P, capital S for the 2, 1, and the 0. So we know we're going to have 3 letters. Then we need to figure out if we have multiplicities like triplet, doublet, singlet. And so that's where we talk about the spins of these things. So the spin of electron 1 is 1/2. We just assume that they're both spin up to begin with, because this series gives us all of the possibilities of spin ups and spin downs. Okay. And then when there's 1/2, minus 1/2, it's 0. And so we have 1 here and 0 here, and there's nothing in between those in terms of subtracting 1. And so those are our spins. Again, that's the capital, the total spin quantum number is the capital S, and then we do multiplicity for those. So when S equals 1, 2S plus 1 equals 3, that's a triplet. And when S equals 0, 2S plus 1 equals 1, and that's a singlet. So triplet and singlet. So triplet corresponds to that, singlet corresponds to that. Triplet corresponds to when they're spin unpaired, and singlet corresponds to when they're spin paired. You could even have spin paired not in the same orbital. And so singlet takes into account all of these possibilities. Okay, and so these are our terms. So we have triplet flavors and singlet flavors of all three of those letters. So we have 6 total terms, and now we do the J values. So this is a nested problem. We have to take each one of these terms and do the J values. And so we have 6 different determinations of the J values. So for triplet D, you need to be able to do this. This is like a subset of the problem. If I give you triplet D, you need to be able to know these things. Right? That should be some easy points. You don't have to do any series or anything like that. If I say you got a triplet D term, what's the total orbital angular momentum quantum number? Okay. And so that would be this 2. I'll go ahead and write that out. Total orbital angular momentum quantum number. Does that make sense to everybody? And then this is the total spin quantum number. So you should be able to pull all of those out of the terms, no matter what term you're given. Okay, so if we have L equals 2 and S equals 1, we go from 2 plus 1 down to 2 minus 1, and so we end up with 3, 2, 1. Notice how it's centered on L. So that's a way to check your work. If we have a triplet D term, D means it's a 2, and so it's going to go 3, 2, 1. Okay. If it was an F, S, P, D, F, F is 3, and so it would be 4, 3, 2. So that's a way to check your work, too. It should be centered on that total orbital angular momentum quantum number. For singlet D, L equals 2 for D, and you only have one option because singlet, the spin is 0, and so you're going to have singlet D2. For triplet P, so L equals 1 for P, and so it should be 2, 1, 0, right? It should be centered on 1, so let's check it. And sure enough, L plus S is equal to 2, L minus S is equal to 0, so our 3 J values are 2, 1, 0. Singlet P, okay, we have J equals 1 because, again, it's centered on that total orbital angular momentum quantum number. And then triplet S, we have L equals 0. And then for an S term, we can't have 3 values. And so it goes from L plus 1 to L minus 1, but it can't be negative, so it's just 1. And so we have singlet S0. Let's see. Yeah, we had triplet S, we had triplet S1, and then singlet S0. So these are all of our terms. Okay. Pretty straightforward, all right? It's a long problem because it's nested, okay? So, you just gotta, it can't be the first time or second time you've done the problem. So practice these. Okay, now let's get into electronic spectroscopy. We combine the atoms using molecular orbital theory and so on, which we're going to get to next in the course. And we come up with these potential energy surface diagrams. And there's a lot of vocabulary in this part of the test related to fluorescence and phosphorescence, intersystem crossing, internal conversion, population inversions, and all of those kinds of things. But I just really want you conceptually to realize what's going on here. We have absorption spectra, and so this is this ground state wave function mapped onto these levels up here. And so notice the center of this ground state wave function is right here. Let's say V prime equals 0, 1, 2, 3, 4, 5. Looks like maybe 6. So it's centered on level 6. 7, 8. Because it's centered on level 6, what does that say about the bond length in the upper state? Like if this is a diatomic. If it were centered on 0, this thing would be right here. It would be right there if it was centered on 0. Right? Because it would be right above it. And these are vertical transitions. Remember, this line goes straight up and hits the upper potential energy curve someplace on this wall. And whatever vibrational level it hits is going to be the strongest transition. And so whenever this 0, so V double prime equals 0 to V prime equals 6, if it's hitting the 6th level, we know that this bond length here, so this is R, I'm going to call it R double prime, and then down here, I'm going to draw this down to the x-axis, this is R prime. You see how the bond length, the average bond length for the excited state is much longer than the ground state because we're hitting this on the wall. If it were 0 to 0 transition was the strongest one, then this bond length would be the same. So we're learning something about the excited state from the absorption spectrum. And the fluorescence spectrum tells us about the ground state. And I'm talking about the electronic excited state or the electronic ground state. Okay. Now, what are these bumps here? This bump here, that bump there. When we see these bumps in the electronic spectrum, what are those? They're transitions for sure, yeah, but what kind? Yeah, they're the vibrational transitions. And so we're going from, let's do a thing. Let's come up here, we'll draw these things straight up, and we'll draw this bar across here. So all of these are originating from V double prime equals 0. And then we could label these with the upper vibrational quantum number. So this is V prime equals 0, 1, 2, 3, 4. You see, every one of these is a different vibrational level in the upper state. 5. See, they start at V double prime equals 0, and they go to V prime equals 0, 1, 2, 3, 4. See, so the primes are really important. This kind of assignment diagram is really important for the next lab, the iodine lab that we're going to do in a week or two. What about the emission spectrum? So we could do the same kind of thing. We could draw this sort of assignment deal, and this is V prime equals 0, dropping down to V double prime equals 0. This next one is, what do you think? V double prime equals 1, right? This one's dropping down to 2. This one right here is 3. This one is 4. This one is 5. Do you see how these are all the lower state quantum numbers? These are the double primes, because that's where they're dropping down to. It's the heads of these arrows right here. What level are they going to? They're all coming out of this V prime equals 0. Why are they all coming out of V prime equals 0? Because of radiationless decay. It drops down really fast and gets rid of all that excess energy, and then it kind of gets stuck in the ground vibrational state of the upper electronic state. And then it all drops down from there. And so what we're detecting is the majority of the signal comes from that V prime equals 0. I mean, there may be one or two molecules out of a million or so that drop from some other level, but it's more probable that they'll go to the next vibrational level, and then they come down here and drop out. So if you understand how to read this, you'll do really well in the next lab. Okay.
I have a question.
Yes.
So for absorption, if it's like more favorable to go to V prime is equal to 6, how come we didn't assign anything to 6 on the absorption side?
Okay, you've picked out the one flaw on this slide, and that potential energy surface doesn't go with this spectrum.
Oh, okay.
Yeah, I didn't have that good of a match. I couldn't find, this was what was given in the Atkins textbook, and they don't have the potential energy surface perfectly matching with the spectrum. Yeah. But that's for real. That would be a big question. We would have many more transitions in this absorption spectrum if it were to match this potential energy surface. Yeah.
If it didn't match, would the highest peak be the 6?
Yes. And so right now, since it's the 2, the highest peak is the 2, then these bond lengths are much closer together. And the minimum of this would be probably, right here, where it's coming up, and you have V equals 1 and V equals 2 right above that vibrational state. Okay. Think of what else I can ask about this. Okay, because this absorption is allowed, we know that the multiplicities of these two peaks, these two potential energy surfaces match. And so it's most of our molecules are spin paired, right? No, not spin paired, but even number of electrons, and so they end up being spin paired. So they're singlets, and so this singlet, so that means this upper state, because there's an absorption spectrum, has to be a singlet as well. And so then we have fluorescence because it's singlet to singlet emission. If we had, say, a crossing to a triplet state, actually, let me draw it lower than this. It's going to get messy, but triplet. What is that crossing called? So like if we see a little crossing right here from the singlet to the triplet state, what's that called? That's a process, one of your vocabulary words. Intersystem crossing, yeah. Okay. And so then we're in this triplet state, and then what would this process be called? Phosphorescence. Okay. And what can you say about its lifetime? Like how long it takes for it to leak out? It has a longer lifetime. Okay. Now our intensities, we talked about this vertical transition. We have the ground state vibrational wave function. And this is a plot of the excited state wave function. So this is the actual, plot of the wave function here for the vibrational levels. And notice how at the turning points, when you get really high in vibrational excitation, they have these large areas at the ends, which gets closer and closer to what we see in just a classical pendulum, where it spends most of its time at the limits and very little time in the middle. And so that's the overlap. So if we were to just take this wave function here and do the integral of, say, let's just do this, d double prime. So 0, and let's say this was 14. All of these are not equal to 0, but which one is the highest intensity? You just look at the wave functions. Notice this isn't quite the same as the transition dipole moment integral, because we don't have light in the middle. Okay, this is just saying that really that influence of light, that's multiplying it by a constant function, f of x equals x, And so it really isn't playing much of a role. It's really the overlap of the vibrational wave functions that gives you the differences in intensities. And so these are called the Frank-Condon factors. So it's an approximation to the transition dipole moment. And that's how you can get those intensities. It's really not this piece that's giving you the intensity, it's this piece. You see, it's right above that ground state. And since they have they have non-zero areas in the same part of the, if you're integrating this overall space, you're integrating over the whole x-axis, and where these functions overlap, that's where you get a large non-zero result. Okay. If you look at the ground state here, it's non-zero here, but that really doesn't overlap with this wave function. And so that's not going to be a very strong transition. The 0 to 0 will be very weak in this situation. Okay. So that's what we're talking about with the Frank-Condon factors. It's an approximation to our transition dipole moment integrals. And then we get to the Jablonski diagram. So I've seen these drawn several different ways. Sometimes they have the singlet S0 go across the whole bottom, so don't be confused by that. So let's see. It might just be a whole block here with these lines across. Okay, and so that whole block would be S0. And then it would have S1 and T1 up here. And so then they could show like the absorption going straight up, and then the fluorescence coming straight down, and the phosphorescence coming straight down. Okay? Does that make sense? Let's walk through the Jablonski diagram and all these different processes. So here we have that. We have absorption, pumps all the molecules up to the singlet. So singlet to singlet. Again, if you had a triplet ground state like an oxygen, then the absorption would be triplet to triplet. You just can't have a spin flip on absorption. Okay, so it's either, there's no corresponding phosphorescence in the absorption. Phosphorescence is emission, fluorescence is emission. Absorption has to be allowed. And so it has to either go singlet to singlet or triplet to triplet, but it can't cross when it does that. So here we have singlet to singlet. And then we have non-radiative relaxation. Okay, and then we have that potential intersystem crossing. So that's this one. This intersystem crossing was next, and non-radiative relaxation. Or we could have internal conversion, which is this one, and non-radiative relaxation all the way down. Yep. We could have a second intersystem crossing here. So molecules can just heat up. They don't have to emit light, fluorescence or phosphorescence. You can hit them with visible light or UV light, and it just warms up the molecule. Okay. Well, you could also have emission events, and so you could have phosphorescence or fluorescence. And since we've used an absorption spectrum, say in the visible range, that's the instrument we're using, and so that's why we call fluorescence and phosphorescence that show up in those same ranges of radiative transitions. We don't count the infrared coming off of these systems as radiative. Okay. And then chromophores. What are chromophores? Well, these are all of these different species that absorb light. So the double bonds, the functional groups, the non-bonded electrons. So we can have these non-bonded electrons be pushed up into a pi star orbital, or they can go from this functional group onto the ring. And this is azulene, but if you put these aldehyde groups on there, then you can make it turn red. You can take that blue transition and you can extend the box a little bit and cause it to shift down. So here's azulene. Nice blue compound. So again, the chromophores here are those pi electrons in this ring structure. You can put fluorines on there and shift the peaks. One thing I would like to show you here is notice how the absorptions on the top and the transmittance spectrum on the bottom. The absorptions go off scale, but the way our eyes work and the way the CIE tristimulus values and everything work, they work in transmittance. And so you can see how things do what we call get saturated. So notice how these peaks, this blue peak, then this one, then the green one's off scale. When we get to the green one, you see how fat it is. It starts to change shape. And this is called saturation. And it absorbs all of that light. So notice we start out kind of a pale pink color, and then we become deep red. Here, this saturation is spreading out in both directions, but there's still this window for blue light to get through it, so this compound is blue. And here, this is really taking out all of the red. We start with a pale green, and we get more and more like almost a blue-purple. All right, so that's everything for the main points on these lectures. We've got time for your questions. So what else do you want me to go over again or clarify for you? I want this to be a good exam for you. The written one is the written out part is the term symbol part. So you got to be really good with that.
Can we look at another term symbol?
Yeah, we'll try to do one quickly. Okay, let's find some. I'm going to just do it right here since I've got a nice open space. Let's do one that's, I'll do one that's a little more difficult than what's on the test, okay? So, and we probably won't finish it, but we'll give it a good shot. So let's do, it doesn't matter what element, but we're going to have a P1, F1, okay? So if you have an element set up where this is the electron configuration ends in P1, F1, then let's go ahead and jump on it. I'm only going to give you a 2-electron system. If we had 3 electrons, it would just be a nested problem even further. It's the same skills, but you do all of the 2 electrons and then you add the third to the results of each of those. It's absolutely tedious. Okay. Someone should write a software package for that. They may have, who knows. So L1 is equal to, let's just go with the first electron. What's the angular momentum quantum number for this first electron? Right, SP. Okay, so it's 1. And then L2, SPDF, 3. Okay, so what kind of letters are we going to end up with? Yep, so we have a 4. And then what's the minimum? Since I've got 1, it goes down to 1 minus 3, but it's absolute value. Okay, so that's going to be 2. So that's equal to 3 terms, 4, 3, 2. Okay, what letters do those correspond to? So S, P, D, F, G. Okay. S, P, D. SPDF, okay, that's an F term. And then SPD, that's a D term. So those are our 3 different types of letters. Excellent. Okay, so then our spin, we have 2 electrons, so we know it's going to be triplet and singlet. I mean, you just, because they can be paired, unpaired or paired. Unpaired is triplet, paired is singlet. So can we just write down 1 and 0? All right. This is spin up. This is spin paired. Okay. Each of them is a half. Okay. And so then that's triplet, 3 and 1. So that's multiplicity. There's no letter assigned to multiplicity. Never have seen it in any of the books. So it's just multiplicity, 3 and 2s plus 1. So we have triplet G, triplet F, triplet D, singlet G, singlet F, singlet D. So we have all of those. Let's take the worst looking one, triplet D, and let's do the J values for that. Okay. So now, since it's nested, we have to pick one, triplet G. So for this one, then we have a particular J range. All right, so for G, L equals 4, right? See that right there? So that's L plus S, 4 plus 1, all the way down to 4 minus 1. I do the mins and maxes. So we have 5 down to 3, 5, 4, 3. So J values are equal to 5, 4, 3. So that gives us these three terms, triplet G5, triplet G4, and triplet G3. And then the next one is the same, and the next one is the same in terms of how you do it. Okay, so it just takes time, but if if you get this far and you start another one and you run out of time, I know you know what you're doing. Okay, so don't be panicked that you can't get all of them done. But you've shown me with very clean and clear work, you know what you're doing, and so that's good. You'll get full credit. Okay. So I think you should be ready. All right. Y'all have a great day.